All right, let's get started. Welcome, everybody. My name is Nathaniel Stevens. I'm the chair of ISEA, the International Statistical Engineering Association, and I'm very happy to welcome Caleb King, our speaker today. I'll give you a brief introduction to who Caleb is and then what his talk is all about. And I think it's a really important talk and an interesting talk, and I think that you guys will all be happy to have listened to this. So Caleb is a research statistician developer at JUMP. He received his PhD in statistics from Virginia Tech, and his research areas and interests include reliability and design of experiments. Caleb is also a member of the ISEA board. And part of what he's going to talk about today is an initiative that he led in the last year, where we put together a working group to kind of consider what are the main challenges and stumbling blocks for statistical engineering and ISEA. What we have collectively come to recognize over the last couple of years is that people struggle with understanding really what is statistical engineering, how does it differ from other problem-solving frameworks, and so Caleb led a working group that really looked into this and tried to come up with some tangible insights. And so part of his talk is to address that, and he's going to weave that into a case study that he's worked on, and hopefully that will illustrate what is statistical engineering, how does it differ from other frameworks, how is it similar, what does it have to offer. So with that, I'll turn it over to Caleb. But before I do, I'll just let you know that you're all in listen-only mode, but if you have questions, there is a question box in the GoToWebinar control panel. Ask those questions, type them there, and I will moderate them. If anything is pressing, I'll interrupt Caleb and ask it in the moment. Otherwise, we'll delay all the questions until the end. So please make sure to use that feature. Okay, with that being said, thank you, Caleb, for being here, and take it away.
All right. Thanks, Nathaniel, and thanks again for the invitation to talk on this important topic. So I'll go ahead and get straight on into it. So start with some introductions, specifically about statistical engineering and ISEA, for those who may not be familiar with it. So what is statistical engineering? Well, if I were to describe it, I'd say that statistical engineering, and I'll use the little SE going forward, so it's a bit of a mouthful, but it's an emerging discipline that's focused on studying the art of statistics and data science. And I'll pop up here, this is actually the formal definition here in the italics, in the quote. So the study of the systematic integration of statistical concepts, methods, and tools, often with other relevant disciplines, to solve important problems sustainably. And what do we mean by all this? Well, the idea behind this discipline is it's not so much focusing on the development of statistical and data science methodology, as in standard statistics that you may have been taught, but rather on how do we effectively put that methodology into practice? How do we actually apply these methods in real life? I think a great example of what kind of gets at this idea is actually a recent post on the AMSTAT community board, and I'll switch over to that real quick. And there was a talk under this topic of modernizing intro to stats, where somebody was asking for help on ideas on how to do this. And one of the examples I gave here, highlighted in this middle paragraph right here, is kind of an example of what's currently kind of taught in stat textbooks and how that might differ in practice. So here we've got a standard significance test. We have medication A, medication B. Is medication B significantly different from medication A? Well, you could go through the process, run the right hypothesis type testing, run the proper analyses, and conclude that, yes, medication B is significantly different. And what he's getting at here is that the implication seems to be, okay, it's different. That means it's probably better, so we should switch. But he points out, well, there's actually a lot more that goes into that. What if medication B is actually a lot more expensive than medication A? Shouldn't that factor into how we roll this out? Maybe we shouldn't just be so quick to switch over. Maybe there's other information. Maybe it was different here. Was that even the point of the study, was to see should we switch to medication B? Maybe there was a different goal to the study. That kind of gets at the idea that statistical engineering is trying to address, is how do we answer these type of questions, not just as a straightforward application of statistics, but what about the bigger picture? How do we actually go about and apply these in actual practice? So I'd encourage you to go visit our website. That's ISEA-Change.org. There's actually a page there that talks about a bit more about statistical engineering, so I encourage you to check that out. At this point, let me continue with the introductions and talk about ISEA. I just mentioned it. We have a website. What is ISEA? Well, ISEA stands for the International Statistical Engineering Association. It's an organization that was recently stood up to help continue, that's dedicated to the continued development of SE. What do we mean by that? There's kind of three main areas that it helps support. One, it's a unifying body for individuals interested in the theory and practice of SE. You're interested in it? Hey, join ISEA. It's actually free to join. So if you're interested, be sure to do so. And we have all these people who are interested in SE. We can help them support conferences, conventions, sessions at conferences and other meetings where we can exchange ideas and experiences about statistical engineering. So you may, if you've attended any conferences recently, you might have seen special sessions on statistical engineering. That's again something that ISEA helps sponsor. And then finally, we're also working towards the creation and dissemination of a body of knowledge for statistical engineering. That can include, we do have a handbook that we have that kind of is starting, that's getting at helping to kind of set up some of the main ideas behind statistical engineering. It could also go so far as in the future, maybe a journal dedicated to statistical engineering, or even guidelines on how to help create curricula for teaching statistical engineering. That's something that ISEA hopes to help support in the future. So that's a little bit about statistical engineering and about ISEA. So now let's get into a bit of the preliminary information. Nathaniel already touched on this in that since its inception, there's been a lot of confusion around what is statistical engineering, what is ISEA? And that makes sense. This is a relatively new thing, although the idea behind statistical engineering, it's actually been around for well over a decade. Ron and Roger have been trying to promote this idea for a while now. It's only recently that we've started to sort of codify it and create an organization surrounding it. But there's still been a lot of confusion. This was clearly evident at a discussion panel we had at our 2021 online ISEA Summit, where we got to see some real responses from people about their thoughts on statistical engineering. And it was a bit concerning. So in 2022, the board commissioned a working group to help say, we need to look into this. Why is there so much confusion around this? What are things that we can be doing to help address these areas of confusion? And as I mentioned, I was the lead for that group. Here are the other members: Allison Jones-Farmer, Ron Snee, Marcus Perry, Jennifer Kinsler. I tried to make sure to get a broad group of folks who either, in this case, Ron Snee actually helped found the idea of statistical engineering, and people who are still relatively new to the idea. So what were our findings? I'll get straight to the point. I'll kind of skip over the 6 months of discussion that we took. And it was pretty back and forth discussion. It actually took us, even us who have been familiar with this idea of statistical engineering for a while, even we struggled a bit with what is this thing? And so we had to address our own concerns. And we kind of converged on two sources of confusion. The first is what I call the perceived lack of uniqueness. That is, one of the biggest criticisms is that this discipline is no different from other fields, like applied statistics or data science, or even some other methodologies like what Informs has, or DMAIC, Six Sigma, any type of other Agile, any type of other methodology. And this kind of makes sense. If you're looking at something that's relatively new to you, you might want to compare it to things that you're familiar with. And by doing so, in this case, people said, but there's really no difference between these. So why do we have this? What makes this so unique? Kind of related to that, again, is that idea of a lack of understanding of what this is, as I already pointed out. If I don't know what this thing is, I'm going to want to compare it to other things. And in this case, there's some aspects of statistical engineering that look very similar to other fields and disciplines. And so the conclusion is, well, it's not really that different. So what exactly is this? Is this a process for solving complex problems? Is it just a way to train better statisticians? What exactly is this thing? So that led to a lot of further discussion. And one of the things we discovered is that these two sources of confusion typically revolved around the nature of the framework that's been proposed in statistical engineering, especially how it relates to the discipline itself and ISEA. Now, of course, there are other areas that could lead to these areas of confusion, but this was one of the primary ones. Is what about the framework? What is this framework thing? So let me show you what the framework is. Here it is. It's 6 phases that one would progress through in solving a complex engineering project. So there's a main label for the phases. There's a brief description kind of unpacking what that means. There's also a little arrow here that's kind of showing you that this is a loop, so it's an ongoing cycle of improvement, not necessarily a one and done process. Now, I've shown it to you. Here's a picture of it. But again, what exactly is it? Well, let's go back and see how is it developed. Well, it was developed through Ronsley and Roger Hurl's personal experience and an in-depth review of problem-solving methods. They looked out based on their own experiences and other methods that they had encountered on how people solve these complex problems, especially those that involved data. So in short, it's essentially a consolidated description of the general flow of these popular processes and methods. In that case, it's actually not unique. That seems like an interesting way to answer the non-uniqueness question, is by saying, yes, you're correct, it isn't unique. And that's because, yes, it's pulling from other from areas. It's a consolidation. It's a consolidated description of these processes. So if you see something that looks very similar to the framework, that's because, well, it is. We should ideally see a lot of similarities between the framework and other processes, even those that we may not have encountered before. In fact, if you were to read the handbook, there's a section entitled The Theory of Statistical Engineering, where it talks about the framework and the principles. And the implication there is that the framework is a theory, specifically a theory about the nature of successful data-informed problem-solving processes used in statistics and data science. That's quite a mouthful, but it's a theory. It's a description. Let's unpack this a bit more. So, for example, how does it relate to the discipline of statistical engineering? Well, it is a theory within the discipline of statistical engineering. One of the common things that we saw people have confusion about is they kind of conflated the framework with the discipline and said, okay, you're proposing statistical engineering as a new process to solve problems. Again, it's not always about the framework. The framework is a theory within the discipline. It is a description, not a prescription. It's not telling you how you should go. It's trying to describe, here's what we think a successful problem method flows. It's a description. It can be a guideline if you don't necessarily have anything in place. It can serve as a guideline, that's fine, but it's primarily descriptive. And so when it correlates and matches up with other types of processes, that is to be expected. We're trying to describe something that's common across all of these. And of course, there's a lot more to statistical engineering than just the framework. There's, of course, the principles, which I'll highlight on the next slide. There's a lot of overlap between the principles and the framework. And there's also this idea of using case studies to improve practice of statistics. That's another big area that we're promoting in statistical engineering, is the use of case studies. Rather than development of methodology, we want to know how it's put into practice. So we're interested in case studies of how people have done this in practice. So again, here's the principles. I've laid them all out here for you. I'm not going to go through them line by line, but you should hopefully see that there's a lot of overlap between this and the framework, which is to be expected. It's again all trying to describe the point of statistical engineering is how do people successfully implement these statistics, data science methods in practice, accounting for the context of the problem, looking at big picture and such. How do they do that? So that we can take that knowledge and pass it on to the next generation of statisticians and data scientists. And so as a way to try and unpack and describe that, they came up with principles. They came up with a framework. This is our attempt to try and describe it succinctly so that we have something that we can then pass on to folks and say, this is a general flow. These are certain principles that seem to appear very often when trying to successfully approach problem solving. So hopefully that was helpful in kind of unpacking what statistical engineering is about. I think another way, of course, is to kind of illustrate it. What do I mean by this? So for the remainder of the talk, I'm going to walk through a case study that I hope will help illustrate the use of the framework and the principles, especially to illustrate its descriptive nature and what I think is a pretty unique application of these concepts. So if you allow me, I'll then transition to the case study, which happens to be on statistical software testing. Now, I will fully admit, this is actually adapted from a colleague's presentation that he performed at Informs. If you saw that, you're going to see a lot of the same stuff here. So there's that. I did make my own tweaks, but I want to give credit where credit is due. So, all right. So let's get into the case study. We're going to be talking about a feature that's very unique to JUMP. And it's called the prediction profiler. If you're a longtime JUMP user, you should be very familiar with this. If not, I definitely encourage you to check it out. I'll give you a visual demonstration of it in a few seconds. It was developed by Brad Jones in 1991 as a graphical tool to visually explore the relationships between multiple factors and responses. And it basically consists of a set of univariate plots that shows the relationship between that factor and the response, or responses if there are multiple responses. I've got a link here, and I can share the slides later, where You can actually find an article that Brad wrote about the profiler. It's been 30 years since he introduced it, at least over 30 years actually. So I definitely encourage you to check that one out. So I've got the link there. Now these plots are interactive. You can interact with them, and it will update as you change the input value for one factor in one plot. It will change both the response and the relationships with the other factors in real time. Now, one of the key uses with this tool is to identify some sort of particular value, what we call a desirability function, which describes what type of value the user is interested in. Most commonly, if I want to optimize the response and I want to find the factor settings that do that, I can use this desirability function to do so. So I can maximize, I can minimize, I can even achieve a particular target value. That's one of the primary uses behind this profiler. So let me give you a visual example. So here's a picture of a profiler with a relationship. That's all well and good, but I work at JUMP, so I actually have the advantage of being able to actually show it to you. So here you can see the profiler again, and I've also got here a desirability function, so I'll explain that in a moment. But here you can see the interactivity in this case, given this relationship. We can see that as I move up and down this curve, the relationship with B is clearly changing, and that's because of the interaction. Same with here, I can get a little more curvy or less curvy. And if I were interested in saying maximizing my response, I've got a desirability function here that shows that I want to maximize it by this increasing line here. So I can go under this red triangle menu, go to optimization, desirability, maximize, and it tells me based on the range of inputs you gave me, set A to 1 and B to negative, in this case, a little bit above -1. We can actually just stick it at -1, and that pretty much maximizes it. You notice it's a little flat there. So that's an example of the profiler. So that's our prediction profiler. Let me get back to the talk. Now, a wrinkle in things is obviously if we have complete open space on which to examine our prediction function, we can then determine what the optimal settings are. A wrinkle in things might be if there are certain constraints on the design region. And one of the ways we specify that is through what's called a disallowed combination. This is a Boolean expression, true or false, and you have to be careful when you think about it. If it's true, that means I'm disallowed. I am not allowed in the region. If it's false, I am allowed in. So it's a bit backwards from what you might expect, but this is what we use to kind of determine what gets disallowed and what doesn't. How do we constrain our regions? So let me give you some quick examples. Here's one that basically says if the product of my two level factors, if the product of their levels is more than 0.5 or less than -0.5, you're disallowed. You're not allowed in. So my design region is basically anywhere where the product falls between -0.5 and 0.5. So that's my allowed region. That's an example of a continuous constraint. There can also be an actual disallowed combination with levels. So in this case, I am not allowing an old machine to have a new part. I don't know why I'm discriminating against old machines in this way, but for some reason I must not allow a new part on an old machine. So I can have any other combination. Maybe there's old parts, old machines, new parts, new machines, but I can't have old machine and new part. That's just not allowed. It can also be more general than that. So for example, it could be describing a polygon. In this case, let's say I've got a polygon that describes the boundaries of, in this case, North Carolina. I can set a disallowed combination that says if your latitude, longitude coordinates fall outside of that polygon boundary, you're disallowed. And so my constrained region is everything within inside North Carolina. So here's an example of, say, a space filling design within the state of North Carolina. So that's an example of a more generalized version of a disallowed combination. Now, what we're interested in is how does that interact with a profiler? Well, here's an example. We have 5 responses, we have 2 3-level categorical factors, and we have disallowed combinations saying that they can't both be at settings L1. If we look at the profiler here on the right, we can notice that this is respected. I set X1 to L1. This isn't even an option, which is what we want. Now, prior to jump 16, that's not what was happening. Unfortunately, there was something happening where you could actually explore that. Well, we finally were able to figure out how to implement that in jump 16. And so now that is something going forward that is respected. Now that we've introduced that into the profiler, we of course have a particular task, which is I want to test this and make sure that it's fully functional with the disallowed combinations. So that was the task that was assigned to the group for this case study is we want to test the prediction profiler with disallowed combinations, make sure it's working. Okay, so now that I've set up our goal, let's actually revisit the framework. And I can tell you then where we started in the framework. I can definitively tell you that we started here. And you said, great, that looks like it's near the beginning of the process. Good. What exact phase did you start with? And I would respond with, are you familiar with the uncertainty principle from physics? This idea that, when you're trying to look for an electron around an atom, you can't find where it is exactly. It's just a probability cloud. It's kind of like this. There's a probability cloud around the phases here. So if you went in at any point, I might be on one phase or another, but in general, I couldn't tell you where. I couldn't tell you which phases we started with and where we stopped and where we're at exactly. We're in this sort of beginning area. So hopefully you see this as an example of how we're comparing the framework to our process. We at least started at the beginning, which is kind of getting at this particular principle, or actually the next one. I'll start with this principle. There's kind of two presented here. One I'll start with is this integration of sound subject matter theory. This gets at the idea of the other relevant disciplines in the formal definition. If we're trying to understand the problem, it's important that we have people from a variety of backgrounds to help address it. In our case, we had a team that primarily consisted of developers and test engineers, but they had a variety of different backgrounds. Here at Jump, of course, a bunch of them had computer science degrees. Some had advanced degrees in statistics. There was operations research, the optimization part, and even bioinformatics and industrial statistics. We've got people with backgrounds in potential application areas. So it was important that we had that. We had people from the DOE group. We had people from the testing group. We had the actual developer of the profiler who was in a different group as well, all coming together to work to address this issue. And then, of course, there's this principle of understanding the problem context. I think this particular principle helps kind of summarize those first three phases. In order to address the problem, you kind of need to understand what's going on. And so let me walk you through the process of understanding this particular problem. We're in the context of software testing. So, of course, what is software testing? Well, here's a couple of answers that you might identify with. Well, software testing is to show the software works as intended. That sounds good. Make sure there are no bugs in the software. No, duh. Yeah, we don't want our bugs in the software. And assure that the software does what it's supposed to do. These are all actually pretty good descriptions of software testing. And they're all completely wrong. Because they kind of approach the problem as showing the software works, leading us to show this. And you're probably already thinking, but that doesn't sound wrong. Isn't that the point of software testing? Let me give you an example from my background in reliability. I've attended conferences where people in reliability engineering have attended, and there's this bit of a tension between them and the engineers who help create the products. Obviously, when people are testing the products, the engineers who created them would like you to show that they work. The reliability engineers want to break it. They want to know, when does this thing fail? When does it fall apart? Of course, the people who built it put a lot of time and effort into building it. They don't want it to break. But those of us in reliability know failures are more informative than success. If something breaks, I can then determine what caused it to break. I can then determine, is this something that could happen out in the field? Can I do stuff to help prevent it from breaking going forward? I don't know the weaknesses of your product until it breaks. And so failures are more informative than success. It's the same idea with testing. There's a quote here that really sums it up. Testing is the process of executing a program with the intent of finding errors. The idea behind testing is the tester's job is to break your feature. They need to find where are the weak points. Where is it going to break down? Again, failures are more informative than success. If I know where it breaks down, I can then work with the developer to fix that, making a more robust product in the end, rather than something that we hope works. So that's the idea behind testing. You're testing for weaknesses, not necessarily testing to show no failure. So what are some of the challenges that a tester might come across? Well, there's three that I'll kind of summarize here. One is this, what we call the selection problem. I want to find the things that break the software. Now, I don't have unlimited resources. I don't have unlimited time. So how do I best spend my limited time and resources to maximize the chance of finding faults while staying within those constraints? So that's the selection problem. How do I select the appropriate test cases? There's a quality problem. As I'm doing my testing, how can I use my testing to inform fitness of use for the profile, in this case, the feature? I don't want to just test and break it for the sake of breaking it. There needs to be information gathered from the breaking. How do I make sure that my testing does that? if something fails a test, can I use it to determine what caused the failure? And finally, there's what we call the oracle problem. Specifically, how do I determine what is the expected behavior? This seems odd that this is a bit of a problem. I mean, somebody developed it. They obviously know how it's supposed to work. How hard can it be to determine the expected behavior? Well, let's explore that. Let's explore that in the context of a prediction profiler with disallowed combinations. So what are some questions that we might want answered? Well, there's some obvious ones. Does the profiler display the constrained region correctly? I pull up my profiler. Do I see the disallowed combination? If not, great. I've passed. Okay, that's expected behavior. Does it only profile allowable regions? That's good to know. Maybe there might be a backdoor way to get to where the disallowed combinations are. I certainly don't want that. Okay, that's something we might need to consider. Do the profile options work as expected? There are certain options that people want with their profilers. There's the obvious maximize desirability. There are things where you can assess the sensitivity of input factors. Do those still work after I've done this? And are they supposed to work after I've done this? How about maximizing the desirability? Here's a tough one. If your background's in operations research, you know how difficult this can be, especially in a constrained space. So not only do you have to know, okay, does the maximized desirability work, but actually the optimal value. That can be a tough one. What is the optimal value supposed to be? Not everything's as straightforward. And finally, lag. Maybe you thought of this, maybe you didn't. I'm using the profiler, but before this, I could maximize my desirability. It takes less than a second. Now that I've got disallowed combinations, maybe it takes 20 seconds. Is that expected behavior? Should I expect you to sit there and say, I gave it a pretty tight constrained space. I'll give it that time to work. Or more likely would be the user's going to come back and say, it takes me 20 seconds. Why? It was a second before. What'd you do? What'd you break? So those are the questions that we kind of need to answer with the oracle problem. It's not always straightforward to determine what is the expected behavior. All right, so those are some concepts about sort of the beginning part of the process. Now let's talk about this phase. This is actually one of the few times where I can point you to a phase, the development of the strategy. So we've kind of talked about the problem, the context, understanding all of that. Now we need to develop a strategy. How are we going to attack this process? And again, relating it to the principles is this idea of developing a problem-solving strategy. So what is our strategy? Well, let's start by saying what other people would commonly do. What are some common testing techniques? So one is what we call unit testing. So this idea I've got this complicated feature. How about I just break it into individual units? Maybe I have a unit that tests the display. In this case, I put in a simple disallowed combination. I run my profile and I look at the graph. Is that disallowed combination present? No, good, it passed the unit test. Maybe there's something for the sensitivity feature. Maybe there's something for the maximized desirability feature. Basically, you break it down into these individual units and you test each unit. And if it passes all those unit tests, you're good. You can think of it as almost kind of like a one factor at a time type thing. There's also this idea of regression testing. In other words, I've introduced something new. Ideally, nothing else should have broken when I introduced it. If something is not working now when it used to work before and it's still supposed to be working, that's what we call regression. We want to prevent regression in our features, so we need some tests to help prevent regression testing. Now, here's a quick quote about where are the bugs. In this case, the person saying, bugs lurk in corners, congregate at boundaries. It's almost like actual bugs. Where are the bugs? They typically hide in the shadows, hide in the cupboards, all these places where you're not going to obviously see them out in the open. This is important to know in testing. It seems commonplace knowledge of course the bugs aren't going to be that easy to find, but it almost seems sometimes when we do the testing that that's not how we go about things. Let me illustrate with some empirical evidence here. So here we got some examples of types of software and software systems that have been tested. And this first column is telling you how many factors are actually involved in a failure. So let's start with the medical devices. Roughly 66% of the failures involved one factor. You would catch those with unit testing. 97% involve two or more, or at least at most two. And nearly all of the, by that point, three or more, you've got to capture a few more. But the majority of them involved around two. For browsers, it's even worse. If you only looked at one factor at a time, you'd catch 29% of the bugs. You would have to look at 3 or more factors to get at least to 95%. Servers, the NASA GSFC, all of these, the point of this is showing you that a lot of your bugs are multi-factor bugs. You can't find them just looking at one factor at a time. You need to consider multiple factors interplaying with one another. And conceptually, this makes sense. These are complicated software. Most of the time, a bug is going to happen because you follow a certain sequence of steps involving multiple inputs, and you get a bug. Something breaks. So our testing needs to reflect that. Our testing needs to be able to capture those multi-factor bugs because that's where most of them are found. And this led us to consider what are called covering arrays, which our DOE developers have a lot of expertise in. Now, if you're not familiar with what a covering array is, I'll start with an orthogonal array, which is a common type of design in design of experiments. An orthogonal array is just an array where for any, if it's strength 2, say, that means for every 2 columns, every combination of levels between those columns occurs the exact same number of times, maybe twice. They all occur twice. The covering array is a generalization of an orthogonal array. It has the same property for any 2 columns, say. I'm looking at the combination of levels, but in this case, instead of happening the exact same number of times, they just have to occur at least once. I can have certain combinations that appear more often than others, but they at least all have to be there, at least present. That's what we mean by covering array. It's a generalization. Now, why are we interested in covering arrays? Let me show you a table. The top row is going to tell you the number of runs in the covering array. The bottom row is going to tell you how many factors it can account for in that covering array. In this case, we're looking at a strength 2 covering array. The beginning, 3 factors, 4 runs, 4 factors, 5 runs, doesn't seem very efficient. But as you keep going, if you have 126 factors, you can generate a covering array with 10 runs. Have 462 up to there, 12 runs. If you have over 1,700 factors, I can give you a covering array that can give you all possible pairwise combinations between those factors in 14 runs. That is insane. Now, of course, these are primarily effective in software testing where our output is deterministic. But again, look at how efficient these are. And that's for strength 2. Now, of course, if I increase the strength, we're going to need a few more runs, but already you can see how powerful this type of tool is. So why covering arrays? Well, that table before shows you that it's incredibly cost efficient. Thousands of factors in less than 20 runs. It also helps address the selection problem. You have a designed way to determine what to test. You're being very systematic about it rather than trying to randomly guess. It also helps address the quality problem. If all of your tests pass at strength T, then you can determine that there are no faults due to T-factor combination. So if I have a strength 2 covering array and every test passes, I know that there are no bugs that involve just 2 factors, at most 2 factors. And as we saw in that first table, that covers quite a few of the bugs. It's also a disciplined approach to testing versus this ad hoc, let's just test more things, or I'll just randomly generate some inputs to test. It's a very disciplined approach. You can see the influence of the design of experiments folks in this. So it's a very disciplined approach to this. Another thing we have to consider in our strategy is the consideration of the data pedigree, which seems a strange question to ask in terms of software testing. What type of data do you mean? We're not analyzing data here. Well, what do I mean by data pedigree? Not only do we need to consider in testing the profile the actual settings of the profiler, but what type of data is going to be fed into the profiler? What types of factors are going to be seen? How many? How many responses are there going to be? What types of disallowed combinations could we see? How many of those? So it needs to be able to handle a wide variety of inputs across a wide range of potential use conditions. How do we test this? We're now concerned not just about the profiler itself, but the data that gets fed into it. Well, here's some suggestions. Maybe we could ask our users for some data sets. I mean, they're the folks who are going to be using this. And we tried, and we weren't too successful. Mainly because some people might have good data, some people might not have good data, some people might have great data that they can't share for proprietary reasons. So, okay, well, maybe we can just generate our own data. Okay, great, that sounds feasible. How do we do that effectively? How do we make sure that we've spanned that space of inputs, that selection problem again? How do we make sure we've covered that? Well, here's an interesting idea we stumbled upon. What if we systematically constructed a set of data tables using DOE concepts? Maybe it looks something like this. Here's a table of factors. There's a factor x1. That's going to tell me whether x1 is a 3-level discrete numeric or 3-level categorical. Factors x2, 3, and 4. I have levels that determine what type of factor that is. I then have another factor that's going to tell me what type of factors are the x5 through x10. Are they categorical, continuous, a mix? How many responses am I going to have? What's my goal? What model? What are my constraints? The run size. Am I going to augment the design? Do I have a simulated model? The bottom 3 actually look at the profiler settings. The rest of these are factors that tell me how do I set up the data table that's going to be used as an input to the profiler. Here's an example of what that output looks like. So just wrap your head around this. We have factors, kind of like in design experiment. But in this case, instead of the factors are settings that determine a single response, my output is a table. It's a particular type of table. So I'm using the design to help me generate data tables that I then use to feed into the profiler. Then I've got some stuff about the profiler settings. This was mind-blowing that you could actually use a design experiment to generate a table that's almost in of itself a designed experiment that we're then going to use as input to a profiler. It's like this meta design, if you will. So that was a key insight into this process. And that again was using that DOE expertise. This is another great example of that principle of integrating subject matter experts from other areas. Okay, so that's all about the strategy. We've got a general strategy on how to develop the test cases. Now, how do we implement that? And in this case, we're in this phase. Again, I have another probability cloud around the final 2 arrows here, because when we implemented this, it was kind of a mix of the tactics and the solution. But we're, again, somewhere near the end here. So let's briefly talk about the test suite. If I tried to do all possible combinations, that's over 1 million test cases, which is a lot. But we have our friend the covering array, in which case we have a strength to covering that can capture all pairwise combinations in 13 runs. We have all these combinations. We can look at every pairwise combination in 13 runs. Again, super efficient. And including that, all 8 combinations of the profiler options are covered as well. So we can cover not only the profiler options, but a wide range of data tables that can be included here as inputs. And one of the things here going into the principles, so we've developed our test suite. Now there's this idea of the sequential approaches that we highlight here in the principles. I point this out because here at JUMP, one of the things we have is a nightly test suite. So we have a suite of unit tests, and every night we run those tests. This means that already we were primed for sequential application. We knew this wasn't going to be a one and done. We already had it in our mind this was going to be sequential. And what was the advantage of this? Because we had the nightly run, every day we could then go back, look at the tests and say, how well did it do? What did it pass? What did it not pass? We can then actually look at the tests and say, are we capturing that behavior correctly? Am I actually capturing the expected behavior so we could maybe revisit and improve the oracles? Maybe there are areas where we needed some random components. We could do that. And then every time we could actually augment that original table of factors, we actually augment it with additional factors. We're essentially doing design augmentation on the fly to help improve that coverage, all because of this nightly running of the test suite. So already it was baked in that we needed that sequential coverage there. Okay, so now here I am kind of at the end of things. Quick summary of the case study. Hopefully I've shown you through this that software testing is not a straightforward task. In fact, deriving oracles is difficult even for statistics software, where you need to handle not only the functionality, but also the numerics, make sure the numbers are right, in addition to the features themselves. Combinatorial testing is an effective and efficient approach. Some of my colleagues, Ryan and Joseph, have been trying to promote these ideas for years, that of combinatorial testing as an effective way to approach software testing. It's much better than one-factor unit testing. Hopefully I've illustrated time and again just how crazily efficient these designs are. And also, finally, that there are significant advantages to treating software testing as a design of experiments problem. A lot of those problems I talked about, the selection problem especially, I have a space of inputs to my feature. I want to make sure I test those features, economically across this big space. That is exactly what design of experiments was designed for. You have a big space of input factors, and you need to be very efficient in how you test that, or determine what are the important factors. That's what DOE was designed for. So it makes sense that it should be applied here. It's perfect fit. And of course, it's a great tool in this case for combining both data set generation and profiler features. So not only just generating what are the factors I need to test my feature, but I can even use it to create the tables, the actual data to input into it. All right, one final thought here at the end. And I hope this, if anything, this is the biggest takeaway you get from this. You notice throughout that when I compared it to the framework, I wasn't always able to point to one exact phase. And that was my point. Case study does not have to strictly adhere to the SE framework to be effective. That is the point I'm trying to illustrate with the use of the framework. You can use it to compare generally. Ideally, the framework should pretty well align. Now, it's not going to align maybe completely. You won't be able to say, we were at this phase exactly, and at this phase, and at this phase. But again, you could kind of see there was a beginning part where we were looking at trying to understand the problem. We developed a strategy, and then we implemented it. The idea is that there should be a lot of overlap because of how the framework was developed. It was based on all these popular, successful problem-solving methods. So ideally, it should kind of match. So there might be areas where it aligns great. There might be areas where it's kind of loose and you have the probability crowd. And there might be cases where it doesn't align at all. And I think those, kind of getting to the idea, the failure idea, those are even more important. Where are places where a framework doesn't align? If your problem works, that's fine. We can improve the theory. It is a theory. There's always room for improvement. And that's where folks like you come in. We're always on the look for good case studies that kind of show how we successfully implemented this process. If it aligns with the framework, great. If it doesn't, I'd say almost better, because now we have an opportunity to revisit and say, okay, what did you do differently? How can we improve our theory and our understanding of how you solve these problems? Again, with the idea we want something to pass on to the next generation. This is something that's sorely missing. This is why Ron and Roger started thinking about this, is because we can teach them the methods and teach them how to do those, but how do we actually put that into practice? How do you successfully do this out in the field? This is what we need to pass on. And so this is where folks like you come in to allow us to get us more information, gather all those case studies so we can further refine our theories and principles going forward. And that's all I have. Thank you.
Well, thank you, Caleb. That was really, really good. There's several people here mentioning in the question box, just thanking you for your talk and how illuminating and helpful that was. Awesome. And so there's a couple specific questions. Before I get to those, actually, I'm going to do this in reverse order. There's one that is sort of a housekeeping question. Will the slides be shared? And I think the answer is yes. We will post these slides on the ISEA webpage, but also all of our webinars are recorded and later posted on YouTube. So you'll be able to rewatch this as well if you'd like. So there's going to be lots of ability to interact with this webinar even after the fact. Okay, so I guess I want to start just by talking about where you ended and began, just this idea of the SE framework as a theory. I think that that's a very valuable and helpful way to look at this. You mentioned it being descriptive, not prescriptive, because I think what a lot of people struggle with is if they think about a case study that they see published, whether it's associated with statistical engineering or ISEA or not, it's easy to ask the question, like, is this an SE case study? And then you might say, well, it's like this chicken or egg problem. Like, how do you know if it was an SE case study, if it was done before this SE stuff was even really talked about? But the way you laid it out, the answer is yes, it could be an SE case study if it adhered to some of these principles, and it might align well in some ways and not in others. And so I just think that's a really helpful way to think about it as a theory that is evolving, and that, like you called for, if there are inputs from anybody, the community, about how this can be refined, we're certainly open to those suggestions. One question I had about the framework. So you mentioned that it's meant to be a theory, it's not prescriptive. Um, but visually that framework is laid out as this kind of sequence of arrows,
Yeah.
and there's an implication there that one step follows another. And you talked nicely about how there's kind of like this probability cloud where like you're kind of in a fuzzy way belonging to all of these at once, depending on your circumstances. I'm wondering if in the particular case study you talked through, whether it really was linear. You know, do you
Mm.
sometimes jump back and forth, even outside of your probability clouds? Like, is there a cyclical nature even within those steps as you refine the problem or as you develop a strategy? I'm wondering if you can talk a little bit about that.
Yeah, I would say absolutely. That rather than necessarily the straight lines, if anything, if I were to go back to that, rather than just the big line coming through and around, I'd have smaller lines looping through each step. I think it'd be a bit of a messier graphic because I could have lines there, I have loops everywhere else. Uh, I have
It's a
loops
fully
everywhere.
connected graph.
So it becomes now more of a mathematical object of this interconnected graph, but that's the
Yeah.
way I kind of see it. So there is kind of a general process flow of kind of that idea of understanding the problem, what it is, wrapping your head around it, and then the development of strategy, and then implementing it. Essentially, if I were to group it, that's the way I kind of group it into those three steps. But again, there's looping back forward through that. You start to develop the strategy and you realize, hey, there's something we missed in the context. So you're revisiting the context, you redevelop the strategy. We go to implement this and we realize there's a certain part of the strategy that's definitely not going to work. Revisit the strategy. So yes, it is a bit of a weakness of the graph in kind of showing that linearity when it actually, yes, it is a lot more involved. But at least in terms of this idea of a general process flow of understanding, develop strategy, implement, I think
Yeah.
that would be kind of the general flow to it.
Yeah.
How that gets broken down and how it puts into practice, that's where things are going to get messy. So
Yeah, yeah, no, I agree. So then, kind of related to this idea of like you can retrospectively look at a case study and sort of assign whether this was a statistical engineering case study or not. I'm wondering if when you approach this, did you approach it in real time through the lens of statistical engineering? Because one of the questions here asks, what did some of your more statistical peers think about the SE framework as you're going through this kind of a case study?
so I would say for this particular case study, this is an example of one where it was more retrospective, looking at
Hmm.
how the framework and principles applied. Because in the heat of it, we didn't actually think about it in terms of that framework. It was just we were working in the context of, so it was actually part of a bigger group. The main initial part of the group was to say, is there a way that we can effectively allow for searching for optimal settings with disallowed combinations in the profile?
Hmm.
And then once there was an idea about how to do that, and then there came the idea of, okay, now how do we test this? And a lot of what motivated that was the experience of my colleagues in the DOE group, where they've been advocating for these techniques in testing. So the use of covering arrays to be more efficient. And I think that was the primary motivator in this project. So we never really didn't actually think about in terms of, okay, we're going to sit down and identify the problem. We're going to sit
Hmm.
down and find the context. I think it was more natural in that. That's just kind of how we approached it. And when when this idea about the special session on statistical engineering came up, that's where we thought of, you know what, this actually would make a great case study. And then going back and visiting and kind of seeing how we kind of aligned, how we illustrated the principles, that's what was the enlightening part, is saying, oh, wow, yeah, just going through this, we didn't even actively think about that. It just came up in the process. And I think that's what's going to happen with a lot of these other case studies and these other methods. Is that's probably how they came about, is you latch onto something, it looks like it works, and you say, okay, how do I repeat this process going forward? So that's how these other methods developed. That's essentially what led to the development of the framework. And the principles is that same idea. You have people
Hmm.
who went through this process, it was very successful. How do we codify this? So that going forward, we can kind of teach other people how to do this. So no one has to reinvent the wheel.
Right.
So that's how I describe this particular process.
Yeah, it's you know, I guess it works. Retrospectively, it works for a reason. You know, like, why was it successful? Well, probably it had elements of what is sort of being referred to as this theory of the SE
Mhm.
framework, because that's how that framework was developed. It was you know, the original founders of this idea saying, like, let's look at all these things that worked well. What were the common
Mhm.
elements?
Yeah,
So yeah, that's really helpful. Like, I think that you know, it's really, it's all about critical thinking. It's about you know, principled statistical thinking through these kinds of data-driven problem-solving efforts. There's a question here. Let me find it again about this specific case study. The question was, how do you efficiently decompose the failed run to find the failing pair of factors?
that is something that I think they're still actively looking into. I forget the term they use for it. Um, but yeah, that is one of the things we thought about when applying the covering arrays is how do we address that. So I know there's some active research on that. I have you reach out to my colleagues Ryan Lekovitz, Joseph Morgan, if you want more info about that. Um, because they're definitely more steeped in it than I am. But that is an active problem. That is one of the things we had to think about when we run this covering array is how do we extract that information? And there are certain cases where it's pretty easy, and there are certain cases where it's not. So I'd say there's definitely active research into at least more effective methods of doing so.
Mm-hmm. Okay. There's one other comment here, sort of going back to SE more broadly, is that the SE they liken basically to critical thinking, which is very difficult to teach, and it requires sort of an integration of tools with the particular situation, and that's not, as is pointed out, easy to teach. But I think, like you said in your talk, that probably the most effective way to learn this is learn by doing, either through, you know, working on and solving problems yourself, or reviewing case studies, you know,
Mhm.
seeing, you know, what are the common elements of success, what are the pitfalls. But I agree, this is hard to teach, and that's something that
Yeah,
ISEA is sort of working on and committed to. That's in part what the handbook is meant to help with, but we are constantly sort of on the look for and developing case studies to help in this way.
exactly.
I think that addresses everything that's come up in the questions. I'll just pause for another minute or so to see if any other questions arise. But while we wait, I'll just echo that there are many, many comments here thanking you for a great job. And I will thank you again. That was a really helpful talk and a really interesting case and a cool application of DOE. I like your idea of the meta DOE, because that's really
Oh
what it
yes,
felt like.
that was the most exciting thing that came out of this
Yeah,
when they proposed. Wow, this meta DOE.
DOE within DOE within DOE.
Oh yeah.
Yeah. Okay, I don't see any other questions coming up here, so I think we can end this, and I'll just thank you again and remind everyone listening that both the slides and the recording of the webinar will be made available on our website. And we are currently planning for the next webinar. It will be later in the spring. We announce these in our monthly newsletter as well as on our website. If you're not a part of the newsletter, make sure you become a member on the website and you'll receive those monthly in your inbox. If you've got any questions or comments, I'm sure Caleb will welcome email feedback from you. And if you've
Absolutely.
got questions more generally about ISEA, feel free to direct those to me. All right, thanks everybody. Take care.
All right. Thank you very much.